Now we can begin ratios. Intro to ratios. What exactly is a ratio? A ratio is a fraction that may compare part to whole or part to part. For example, suppose in a class the ratio of boys to girls is 3 to 4. What does this mean? It means that the number of boys divided by the number of girls is a fraction that, in its simplest form, equals 3 over 4. This is one of the tricky things about ratios. The test will always give you ratios in their simplest form, and essentially always the absolute number of participants will be larger than the numbers in the ratio. So for example, ratio of boys to girls is 3 to 4 could possibly mean that we have 15 boys and 20 girls, or 21 boys and 28 girls, or 75 boys and 100 girls, or 300 boys and 400 girls, or 3,000 boys and 4,000 girls. In other words, we have no idea simply from the ratio what the absolute size of the group could be. The absolute size of the group could be anything. For some positive integer n, we definitely have 3n boys and 4n girls. We can definitely say that if we're given a 3 to 4 ratio. Here n is sometimes called the scale factor. Notice if we're given, once again, if we're given a ratio 3 to 4, we have no idea about the absolute size of either group. That's a big idea to which we will return. There are many different ways of presenting ratio information. The first, I'll call it P to Q form. The ratio of boys to girls is 3 to 4. We just spell it out literally like that. Second is fraction form. The ratio of boys to girls is 3/4. We can write it as a fraction. Third is colon form. This is very common on the test. The ratio of boys to girls. We read this as 3 to 4, but it's written with a colon. And then finally, a tricky one, I'll call this idiom form. For every 3 boys, there are 4 girls. So that's an idiomatic way in English to say exactly the same thing. All 4 of these contain exactly the same information. Now, of course, of these 4 forms, the most useful by far is fraction form, because when we rewrite the ratio in fraction form, then we can do math with it. Notice, in all of these, order is important. If we talked about the ratio of girls to boys, all the numbers would have to switch. So if we had girls to boys, that would be 4 to 3 or 4/3, something along those lines. To solve the majority of ratio problems on the test, we set 2 equivalent fractions equal. This is an equation of the form fraction equals fraction. An equation of this form is known as a proportion. And if you're not familiar with the mathematics of proportion, what you are allowed to do and what you're not allowed to do with proportions, I highly recommend watch the video Operations with Proportions. In particular, we often set the given ratio, the ratio given in the problem, equal to a fraction of the absolute quantities. So for example, here's a practice problem. In a class, the ratio of boys to girls is 5 to 8. If there are 40 girls, how many boys are there? So I'm going to suggest pause the video here and work this out on your own. I will say this is probably a simpler problem. Probably this is a little too simple by itself to be a test problem, but this skill could be part of a larger problem. This definitely could be a piece that you'd have to figure out as part of solving a larger test problem. So what I'll say is we solve by rewriting the ratios in fraction form and setting up equivalent fractions. So one fraction, of course, is 5 over 8. That's given. And that's a ratio of boys over girls. So I have to make another fraction of the form boys over girls. I have an expression, I have a number for the girls, 40, so I'm going to have to say that the number of boys is x. So that fraction would be x over 40, boys over girls. So x over 40, boys over girls, equals 5 over 8, boys over girls. Make sure that both fractions, the numerators and denominators, represent the same things. Well, in this particular proportion, I notice there's a multiple of 8 in both the denominators. So I can cancel that multiple of 8. with what we've called horizontal cancellation. Once I've done that, then I'm free to cross multiply. I get 8 equals 25, which tells me there are 25 boys in the class. Here's another one. In a class, the ratio of boys to girls is 3 to 7. If there are 32 more girls than boys, how many boys are there? So again, I'll recommend pause the video, see if you can work this out on your own, and then I'll show the solution. Now, some people may be tempted to use algebra to solve this. So, for example, one could assign variables. B is the number of boys, G is the number of girls. We could set up two equations, B over G equals 3 over 7, G minus B equals 32. We'd have two equations with two unknowns. We would be able to use algebraic techniques to solve this, but that would be very long and time-consuming. So I would not recommend that particular approach. Instead, I'm going to show something much simpler. I'll just point out ratio information often allows for a number of elegant shortcuts. Here, I'm going to say, let's rewrite the given information in terms of scale factor. The fact that we have a ratio of 3 to 7 means we could say the number of boys is 3n, the number of girls is 7n. We don't know what n is, but in other words, we can rewrite this in terms of n. Well, then it's very clear that the difference, 7n minus 3n, is 4n. 4n equals 32. Well, immediately we can solve for n and then solve for the number of boys. So that's a much more elegant solution. Scale factor is the magical link between ratio information and information about full quantities. This is a powerful shortcut about which to know. So far, we have talked only about ratios among the parts, but if we have a ratio term for each part, we can figure out ratios to the whole. For example, boys to girls is 3 to 5. Boys are what fraction of the whole? Well, one way to think about this is that boys are 3 parts of the class and girls are 5 parts of the class. So together there are 8 parts. Thus, boys constitute 3 parts of the total 8 parts, or 3/8. This is sometimes called portioning. Also, so far we have been talking about collections with only 2 sections, boys and girls. In fact, real collections of people and things may have 3, 4, or any number of categories. While hundreds of categories might be possible in the real world, the test will not make you deal with more than 3 or 4 categories. The test will always present ratios of this kind in colon form. For example, general purpose concrete is created using a 1 to 2 to 3 ratio of cement to sand to gravel. If we have 150 kilograms of sand available, how many kilograms of concrete can we make? Assume we have more than enough cement and gravel. So again, I'll say pause the video and see if you can solve this on your own. So the first thing I'll do to solve this is think about proportions. We want to relate sand, the part, to concrete, the whole. So there's 1 plus 2 plus 3 parts. That's 6 parts in the whole. So sand to the whole is 2 to 6. Sand to concrete is 2 to 6, and we can simplify that as 1 to 3. Sand accounts for 1/3 of the total weight of the concrete. So now we can set up a proportion. We have the fraction 1/3, and we can set that up to sand, which is 150 kilograms, over X, the number of kilograms of concrete that we don't know. We cross multiply, and we get 450. So we can make 450 kilograms of concrete given 150 kilograms of sand. In summary, we talked about ratios and a little bit about what they mean and what they don't mean. In particular, they don't mean anything about the absolute size, the absolute quantities. We talked about the scale factor, a very powerful shortcut. We talked about the various notations. Fraction notation, of course, allows us to do math with the ratios, which is very important. We talked about using scale factor notation to simplify calculations, especially involving sums and differences. We talked about ratios of parts to whole, the idea of portioning, and we talked about ratios with 3 or more terms. Combining ratios. Sometimes between different subgroups in a problem will give separately expressed ratios, and we'll have to relate these different ratios either to the whole or to absolute quantities. So, for example, there might be sets A, B, C, and D, and instead of giving us an overall ratio, it might tell us one ratio from A to B, another ratio from B to C, another ratio from C to D, and then we have to combine those ratios to understand what's going on with the whole group. So before we begin this discussion, a few reminders. Number one, of course, we write ratios of fractions, and what that means is we can find equivalent fractions. All the laws of fractions we can use for ratios, and so that's a very helpful thing to keep in mind. Also, we can write any ratio in what I would call algebraic terms. So if we have a ratio of AB equals 3 over 8, that means for some n, we can write 3n, A equals 3n and B equals 8n. And sometimes setting things in terms of the algebra, then that allows us to set up algebra and solve. So that's one possible strategy for ratios also. Finally, a very important point, what we can and can't cancel in proportions. This is just a brief review. Of course, we can cancel up and down in any proportion. We also can cancel across two numerators or across two denominators. All those are fine. The one thing we're not allowed to do in a proportion is cross-cancel. Now, this is something absolutely new to you. I strongly suggest go back and watch the lesson Operations with Proportions before watching this lesson, because if you're unclear on the math of proportions, there's a lot in this lesson that could confuse you. It's very important to be very clear on what you can and can't do with proportions before you watch this lesson. Okay, let's start talking about these ratios. So the combining ratio scenario, what we're talking about in this lesson, occurs when we're given two or more separate ratios within a larger group. Say in a group with type 1, type 2, and type 3, we might be given one ratio for type 1 to type 2 and a whole other ratio for type 2 to type 3. So if we want to understand what's going on in the whole group, we'd somehow have to combine those ratios. We have two basic strategies for approaching such questions. One strategy would be to find equivalent fractions for each ratio so that the common term comes to be represented by the same number in both ratios. So if we have one ratio from type 1 to type 2 and another ratio from type 2 to type 3, we'd want to find equivalent expressions for both ratios so the type 2 number is the same in both ratios, and that would allow us to put it together in one big ratio, type 1 to type 2 to type 3. We'll have some examples of this in this video. The other strategy, and this is especially true if we have to find individual values, individual quantities, how many people in type 1 or in type 3, something like that, then it's much more advantageous to use what I was calling the algebraic approach, where we actually represent the different terms in the fraction. If we're given, for example, 3/7, we represent that as 3 over n and 7 over n, that sort of thing. So here's a practice problem. Pause the video, work on this on your own, and then we'll talk about how to solve this. Okay, so notice we're given two different ratios, and all we're being asked is fraction information. In other words, there's no concern here about total number, how many sophomores, how many juniors. We're only concerned with fractional information, and so that means we can stick entirely with ratios. So it makes sense to use the first strategy. We're just going to identify the common element and find equivalent ratios so the common element is equal. So right now we have two ratios, sophomores to juniors, juniors to seniors. Obviously juniors are the common element. And so we'd like to find equivalents so that the 3 in the first ratio and the 5 in the second ratio are the same. And of course the easiest way to do this would be to multiply the first ratio by 5 over 5, multiply the second ratio by 3 over 3. Then we get these equivalent fractions. Juniors are now represented in both by 15, so now we can put everything together in one big ratio. sophomores to juniors to seniors, 10 to 15 to 18. Now that's a ratio. It looks like you might be able to cancel something, but there's actually no way to reduce that. There's no number that is a common factor of all three of those numbers. And so that is our combined ratio. And of course, if sophomores are 10 parts, juniors are 15 parts, and seniors are 18 parts, we can find the whole just by adding the parts. The whole is 43. And so this means that sophomores to the whole would be 10 over 43. And so that one we can find purely from strategy 1, just combining the two ratios, finding equivalent fractions. Here's problem number 2. Pause the video and then we'll talk about this. Okay, in this one we're given two different ratios. We have three groups, we're given two different ratios, and we're actually given an absolute count. We're told there are 27 programmers, and we want an absolute count. How many customer service reps? And so here, because we're given an absolute count and we want an absolute count, this makes it ideal for solving in terms of the absolute quantities. In other words, the algebraic approach, where we're going to use n. So the first thing we're going to do is, let's say we have P over M, and in fact we don't even need the M. We can solve directly for the numbers here. Programmers to marketers is 3 over 8. We're going to we know the number of programmers is 27, so we can simply find the number of marketers. Marketers, remember, is the in-between term, the term that we need to get from one ratio to the other. That's the common term. So we need to solve for marketers. And here, this is where operations with proportions come in. Before we cross multiply, notice that we can cancel a factor of 3 in the numerator. So we cancel that. We get it down to this fraction. Then we can cross multiply very easily. M equals 72. There are 72 marketers. Now we take that number and use it in the other ratio. The ratio of customer service reps to marketers is 2 to 3. And we know marketers is 72, so C is going to be the number of customer service reps. That's the answer we're looking for. Again, we can cancel. We can cancel now in the denominator by a factor of 3. It simplifies to this. We cross multiply, and we get that there are 48 customer service reps. And so that's the answer. This is a slightly harder problem. Pause the video, and then we'll talk about this. Okay, so what we have here are a few different ratios. We have a cup of butter for a number of cookies, cup of sugar for a number of cookies, and then what we're looking for is a difference. So we're not looking for how many cups of butter or how many cups of sugar. We're given this odd piece of information, 5 more cups of sugar than of butter. So this is a tricky one. This is actually going to require us to use both strategies. So first we're going to have to come up with the ratio, the combined ratio for the whole thing. So we're going to start out, so here we're going to use both strategies. First, we're going to combine the ratios. So these are the separate ratios. Butter to cookies, 1 to 12. Sugar to cookies, 1 to 8. The common factor here are the cookies. And so we have to figure out what can we multiply by. And so what is the least common multiple of 8 and 12? Of course, it's 24. And so we have to multiply the first one by 2 over 2 and the second one by 3 over 3. And this allows us to get this combined ratio, 2 to 3 to 24. All right? Now that we have the combined ratio, we're going to use algebra. And so this means that the cups of butter are 2n. The cups of milk are 3n, and the number of cookies is 24n. So if we found the value of n, we'd be all set. In other words, if we found n, we plug into that last equation and we're done. So now we can use this very strange piece of information. He used 5 more cups of sugar than of butter. So 5 equals cups of sugar minus cups of butter. That's the basic equation we have. Well, now we have algebraic expressions for both of those expressions. So it's going to equal 3n minus 2n. Well, then this becomes very simple. 3n minus 2n is just n. Now we have the value of n. We plug that into the expression for the number of cookies. 24 times 5, of course we can use doubling and halving. That becomes 12 times 10, which is 120, and that's the answer. He made 120 cookies. In summary, one method is to find equivalent ratios so that the common terms are equal in both expressions, and then combine them. And this is most useful if what we're looking for is purely ratio information. Another method, if we're given an actual count, then we can solve for individual values, and then we can either use the algebra or solve directly for the values. And sometimes we have to combine both of these methods, especially if you're given information about a sum or a difference of two different groups. And if you can solve it in more than one way, it's always good to practice and make sure you can do that, because it's always a good thing to have more than one option for solving a problem. Ratios and rates. Rates are ratios. Any ratio with different units in the numerator and denominator is called a rate. To solve most questions involving rates of all kinds, all we have to do is set up an equation of the form ratio equals ratio. We just match the units on each side. Remember that such an equation, fraction equals fraction or ratio equals ratio, is called a proportion. And if you're not familiar with it, it may be a good idea to go back and look at the video, Operations with Proportions, what you can do and can't do with a proportion mathematically. That video is in the fraction module. Rates are often expressed as so many units per units. So for example, all of these are rates. Many of these are drawn from science. The last two are special kinds, 60 minutes per hour or 360 degrees per revolution. These are examples of unit conversions. So these would be examples of things you would actually be expected to know. The other ones you would not be expected to know, but you would be expected to know that there's 60 minutes in an hour, and you can write this as a ratio. We would set this given rate equal to a fraction with the same units in the numerator and the denominator. So either the problem itself would give you one of the rates, for example, one of the blue rates, or you would know yourself something about the units and the way that the units are related. You set that up as a ratio, and then you set that equal to a fraction on the other side that matches the same units in the numerator and the denominator. Here's a practice problem. Pause the video, and then we'll talk about this problem. Okay, so this problem gives us a rate. It gives us the rate of 8 grams per hour. So that has grams in the numerator and hours in the denominator. So we're going to set this equal to a fraction on the other side that also has grams in the numerator and hours in the denominator. We're going to have 30 grams in the numerator, and then we're just going to have a variable, I'll call it h, in the denominator. That's the unknown number of hours. The first step I'm going to do to simplify is I'm going to divide both sides by 2. So I'm going to divide the 8 by 2 and divide the 30 by 2. If that operation is an unfamiliar operation, if you're kind of shocked by that or didn't know that that was a possible thing to do with proportions, I highly recommend that you go back and watch the video, Operations with Proportions. Again, that video is in the fraction module. At this point, we'll cross multiply. Then to get the h by itself, we'll divide by 4. We get h equals 15 over 4 hours. Write this as a mixed numeral, 3 3/4 hours. We're asked when, which is actually a clock time. So we started at noon. 3 hours later would be 3 p.m. 3/4 of an hour is 45 minutes. So that means it's completely melted at 3:45 p.m. Here's another practice problem. Pause the video and we'll discuss this. A bumblebee's wing flaps 1,440 times in 8 seconds. So that's essentially a ratio. We could say it's 1,440 flaps per 8 seconds. How many times does it flap in a minute? Well, first of all, let's simplify that a little bit. 1,440 flaps in 8 seconds. I'm going to divide by 2. That gets me down to 720 over 4. Then I'm going to divide by 2 again. That gets me down to 360 over 2. And then I'm going to divide again. That's going to get me down to 180 over 1. So there are 180 flaps in 1 second. Well, we want the flaps in a minute, so clearly what we're going to have to do is multiply by 60 seconds, because there's 60 seconds in a minute. So the total number of flaps is going to be 180 times 60. We don't actually need a calculator for this. Let's think about this. Let's drop those zeros and make things a bit simpler. If we're doing 18 times 6, well, one way to think about this, the 18 is 10 plus 8. Well, I can do 6 times 10, that's 60. I can do 6 times 8, that's 48. I can add those two, that's 108. So now we're just going to add the two zeros, and so what we get is a product of 10,800, and that is the number of flaps in a minute. Here's another practice problem. Pause the video, and then we'll talk about this. Okay, this is very tricky. We have a couple rates. We have the 20 grams per centimeter, we have the $50 per gram, and then we have this initial starting amount, the starting volume, which is 2 centimeters cubed. So first thing I'm going to do is I'm going to start there. I'm going to multiply those out, and I get 8 cubic centimeters. Well, I want to multiply that by a rate so those cubic centimeters cancel. So I'm going to multiply it by that first rate, 20 grams per cubic centimeter. That way the cubic centimeters will cancel. Then I'd be left with grams. Now I want to multiply something so the grams cancel. If I multiply now by 50 grams, $50 per gram, then the grams cancel, and I'll be left with units of dollar. And that's what we're looking for. We're looking for the price. So I'll point out here, this is actually very easy now because 20 times 50 is just 1,000, times 8 is 8,000. So that would be worth $8,000. In summary, when you see problems with rates, remember you can set up proportions. Always remember to make sure that the units of the numerator and denominators match.